Today we are going to focus on a critical aspect of blast furnace operation, the impact of silica. Understanding its influence is key to efficiency and cost control. We will walk through its effect on slag, consumption, productivity, and quantify its precise impact. Our topic is the impact of silica on blast furnace operation, and we will cover everything from slag chemistry to quantitative effect, providing a comprehensive understanding of this vital component. Now, coming to our uh, next slide, which is about a slag chemistry and fluxing requirement. So let's begin with the slag chemistry and fluxing requirements. As you must be knowing, silica is one of the four major constituents of blast furnace slag, typically making up 28 to 38% of its volume. To achieve desirable liquid slag properties and effective desulfurization, silica must be fluxed with basic oxide like calcium oxide and magnesium oxide. These basic oxides are essential because they help to break up the strongly bonded network formed by acidic oxides such as silica and alumina, thereby decreasing slag viscosity. If the burden leads to high hot metal silicon, slag basicity might increase, potentially causing high slag liquidus temperature and even solidification. In such cases, a reduced slag basicity, often by adding siliceous component, is needed to maintain liquid slag property. Now coming to our next slide, which is related with slag volume consideration. An increase in silica content in ferrous burden directly leads to an increase in total slag volume. This happens because additional flux like CaO and MgO must be charged to maintain suitable slag basicity and fluidity, further adding to slag volume. A low slag volume is generally desired for efficient blast furnace operation. Furnaces using 100% low silica pellet, that is below 2.5% silica or even below 1%, those are very acidic in nature, can achieve the lowest slag volume, contributing to a stable high productivity and low coke rate. In contrast, sinter typically contain 3.5 to 5.5% silica. Now coming to the coke and coal consumption. Moving to coke and coal consumption, a major cost factor, a higher slag volume means more material need to be melted, which require more heat. This extra heat is primarily supplied by increased coke consumption. Furthermore, coke and coal ash primarily consist of acid component like silica and alumina. Higher ash content in injection coals, which can contain around 50% silica, necessitate a higher primary slag basicity in the cohesive zone, which can negatively impact the melting of the ferrous burden. Finally, let's talk about blast furnace productivity. Our sources clearly state that increased slag volume has a negative impact on furnace productivity, which generally deteriorate with increasing slag volume. Now let's get quantitative. We will quantify the impact of 1% increase in silica in total ferrous burden using a step-by-step calculation methodology from the provided source and reference furnace data. First, we calculate the additional silica input. A 1% additional silica in burden means 1% of the total ferrous burden weight, that is let it be 1570 as we did in calculation of alumina. So 1570 kg per ton hot metal, if we consider, then this ferrous burden weight is adding a additional silica. So additional silica equals 0.01 multiplied by 1570, giving us 15.7 kg silica per ton hot metal. Next, we determine the initial absolute silica already in the slag. This is, let it be 250 per ton hot metal. This is the reference slag rate taken, and it has also taken in calculating alumina impact earlier presentation, and this multiplied by 0.345, that is the reference slag silica concentration, which gives 86.25 kg silica per ton hot metal. Then the new total absolute silica in slag is the sum of these, that is 86.25 kg per ton hot metal plus 15.7 kg per ton hot metal, equating 101.95 kg silica per ton hot metal. To accommodate these increased silica and maintain stable slag chemistry, the slag volume must increase. We assume the target silica concentration in the final slag remains at its reference level of 34.5%. Therefore, new slag volume is calculated by dividing the total absolute silica, that is 101.95 kg per ton hot metal, by reference slag silica concentration, that is 0.345, resulting in 295.51 kg per ton hot metal. From these we calculate the increase in slag volume. This is 295.51 kg per ton hot metal minus the reference slag that was taken 250 kg per ton hot metal, giving a slag volume increase of 45 plus kg per ton hot metal. This aligns perfectly with the source's statement that slag volume increased by 40 to 50 kg per ton hot metal for 1% additional silica. So this we have to aid in memory also while calculating the impact of incremental value in silica or alumina in the ferrous burden, or in the coke ash. So volume increased by 40 to 50 kg for 1% additional silica. This is the final bullet point that emerged from the calculation. Now, with the increase with the slag volume, let's estimate the impact on coke consumption. The sources state that for an increase in slag rate of 40 to 50 kg per ton hot metal, coke consumption in the blast furnace increased by 2 to 2.5, that is 40 to 50 kg per ton hot metal. Incremental in the slag leads to, we have to supplement our coke consumption by 2.5 kg per ton hot metal. Taking an average, our calculation for increase in coke rate is approximately 2.28 kg coke per ton hot metal. Additionally, the sources specify that coke breeze consumption in the sinter process increased by 1 kg per ton hot metal for a 1% additional silica in the burden. Finally, let's quantify the impact of blast furnace productivity. The sources indicate that productivity decreases by 0.05 for an increase in slag rate of uh, 10 kg per ton hot metal, using our calculated slag volume increase of 45.51 kg per ton hot metal. The productivity decrease is multiplied by 0.05 ton per meter cube inner volume for 24 hours, which equals 0.23 tons per meter cube inner volume 24 hours. This is a significant drop in production capability. So we can say that what are are the key takeaways for blast furnace steam from the quantitative exercise? Even seemingly a small 1% increase in silica in ferrous burden can lead to a measurable and undesirable consequences. First, increase operating costs due to higher fuel rates. Second, reduce production efficiency from lower productivity. And third, greater strain on raw material handling and charging system due to need for more fluxes. And finally, the potential for process instability if slag properties are not meticulously managed. So coming to the our summary part, to summarize the BF training team, an increase of 1% silica in the ferrous burden equivalent to 15.7 kg silica per ton hot metal for our reference furnace would lead to several operational impact. A significant increase in slag volume. The total slag volume would increase by approximately 45 kg per ton hot metal from 250 to 295. So we can say that 1% silica incremental value leads to addition of a 50 kg slag with your slag rate, whatever existing reference is there, you have to add to 50 kg for each 1% silica to maintain a proper slag chemistry and fluidity. This means more material to melt and handle, increase coke consumption, as we have also discussed regarding this in earlier slide. uh, so the larger slag volume would require more heat, leading to increase in coke consumption in the blast furnace of approximately 2.3 kg per ton hot metal. Incremental value we have to take in coke to supplement this 45 to 50 kg slag melt energy potential. So increased sinter coke breeze consumption also has got an impact. The sinter plant would need to increase coke breeze consumption by 1 kg. So 1 kg at sinter plant, around 2 kg at blast furnace. This coke value, this coke value is to be supplemented. Now coming to the our almost the last slide, which is about the summary. We can say that our reduced blast furnace productivity, consequently the furnace productivity will decrease roughly by 0.23 ton per meter cube, inner volume 24 hours, need for additional fluxes to manage